Okay, so last time we spent a good deal of time kind of introducing this idea of particles, what particles are made of. What do I mean when I use that word particle? We ended up saying that particles are atoms, which are building blocks, and they can be arranged in different ways to make molecules, to make ionic crystals, things like this. We talked about how to classify matter into pure substances, compounds or elements, or into mixtures, and we talked about different properties of matter. Things like density, mass, volume, chemical properties, physical properties. So now we're going to get really into the details of all of this and begin talking about atoms, what they are, the fact that atoms themselves are made of smaller particles, smaller building blocks, etc., etc. So let's begin. Atoms. These are tiny building blocks of matter. Every matter is made of some type of atom, and they can be arranged in different ways to create different substances. Two important words that you've already heard, but here I'm finally defining them. An element is just a specific type of atom, so examples are oxygen, hydrogen, carbon, nitrogen. Those are specific types of atoms. And then a compound is a group of atoms that have been bonded together in a specific arrangement. So examples of compounds would be like water, H2O, salt, NaCl, sugar, which is a compound of carbon, hydrogen, and oxygen, things like that. It turns out that atoms themselves are composed of even smaller particles, which we refer to as subatomic particles. Let's start talking about these subatomic particles. Subatomic, that word, that prefix sub, meaning that we're below the level of the atom, so even smaller than an atom. And there are three types: protons, neutrons, electrons. You guys probably know a lot of this already. Protons, sometimes we call them P+, because they have a positive electric charge. So they're positively charged. That's one of the most important properties about them. Where does that electric charge come from? What is it? I'm not able to answer that, actually. It's just a property that protons have for some reason. The mass of a proton is defined as 1 AMU. This is a new unit for mass that we're using, and it stands for atomic mass unit. Protons are so tiny. You guys have got to understand that we're talking such a tiny scale that chemists did not want to use the normal unit for mass, which is gram, because a gram is too big. Protons are incredibly tiny. So instead of saying that they are some fraction, some tiny, tiny fraction of a gram, chemists just say that one proton is defined as 1 atomic mass unit. That is the mass of a proton. Protons are located in the dense core of the atom called the nucleus. Neutrons have this symbol N with a 0. They're called neutrons because they are neutrally charged. They have no charge, 0 electric charge. They have a mass of about 1 AMU. Their mass is actually a tiny bit bigger, but it doesn't make a big difference. And they are also located in the dense core of the atom or the nucleus. So far, a picture of the atom is like this. We have protons stuck together, these particles stuck together in the nucleus of an atom. And then we also have stuck in there, we have some neutrons, like that. And we would call this densely packed region, which would have a positive charge overall, because the protons are positive, neutrons are 0, neutral. We call this densely packed, positively charged region the nucleus of the atom. Electrons, lowercase e with a minus. These are the first subatomic particles to be discovered by a guy named J.J. Thomson. Once again, the history is fascinating, and I wish I had time to talk about it. They are negatively charged. They have an incredibly tiny mass, about 1/2000th the mass of a proton. So we really consider, we pretend like the electrons are massless, that they don't have mass. In reality, they do. It's just very small. And electrons are located around the outside of the atom. So the electrons are somewhere out here. And exactly where the electrons are and how they work has caused scientists a lot of confusion, especially at the beginning of the 1900s. Once again, I can't get into the history of it. But at one point in time, scientists believed that the electrons kind of orbited around the nucleus like planets around the sun, something like that. And you guys have probably seen pictures like this before, where the electrons are shown as kind of moving around like planets around the sun, but that is not the actual correct picture, as we will see. So here's a simplified version of this. The protons and the neutrons compacted here in the middle of the nucleus, and the electrons around the outside. In reality, these electrons do not kind of orbit nice and neat around the nucleus. Electrons are actually very, very, very strange. Whenever we get down, scientists have discovered, whenever we get down to this level, to something this tiny, to this size, um, it turns out that the difference between a particle, a little piece of matter, and a wave kind of disappears, and these things become particles and waves at the same time. And it's really difficult to say where a wave is because a wave is kind of spread out in space. So it ends up being very, very difficult to say, hey, there's the electron right there in the atom. It's very, very strange. In addition, we've discovered that we really can't know much about the location of electrons in an atom. The best we can do is understanding the probability of where they are and where they are not. So instead of saying, hey, the electron is a particle and it's located right there, we say the electron is a wave and it is located somewhere in this region of probability. And all that is very complicated. Once again, we don't have time to get into it. In reality, this is what those regions of probability look like. This is just a computer model. I know it looks very fancy, like glowing bright, but wherever you see the bright spots, those represent very, very high probability of finding an electron. Wherever you see darker spots, those represent low probabilities. And right in the middle is the nucleus of the atom. So you can see that because electrons behave like waves, and because all we can know about them is probabilities, it becomes very, very funky to define and to talk about. So electrons are really found, yeah, they're found on the outside of the nucleus, but in these regions of probability that we refer to as orbitals. So electrons are found in orbitals. We'll talk more about electrons in a little bit and where they're found in the atom. Turns out we can get kind of specific about these orbitals, and we can know some things about where the electrons probably are located, what these regions of probability are like, and where they are in the atom. This kind of summarizes that an electron is not a particle zipping around the nucleus. A simple way of talking about this, and thinking about this is that the electron is sometimes we call the electron as a cloud, the electron cloud around the nucleus. So here's the tiny little nucleus, and yes, the nucleus is incredibly dense, denser than this even. If this was to scale, you wouldn't even be able to see the nucleus. And the electrons are somewhere out here. And all those regions of probability kind of add up to what we refer to as this electron cloud, this cloud of electrons, or excuse me, this cloud of probability of where electrons might be. Ah, yes, the periodic table, one of my favorite human accomplishments ever made. This table never ceases to amaze me. So let me tell you what this is. This table is a list, an organized chart of all the known elements. Some of them occur in nature, most of them occur in nature. Some of them we've had to create in the lab. It turns out once you get, I believe it's heavier than lead, once you go past lead on the table, elements tend to not occur very naturally, at least not in a large abundance, and you end up having to kind of synthesize them in the lab. Some of them do occur naturally, like uranium does, neodymium does. Others, like promethium, do not. Anyway, the table is an organized chart showing all the elements of the universe. Remember, elements are a specific type of atom. So this is the blueprint of the universe, really. What is the universe made of? What is your body made of? What is your dog made of? What is the air that you're breathing made of? Your computer, what is it made of? Remember, chemistry is the study of matter and how matter changes. So this is the key to matter, to how matter works, to what it is. This is a list of all the types of atoms, all the types of building blocks that everything is made up of. For example, your body, the cells in your body are mostly carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, and then very, very small amounts of things like iron, calcium, potassium, sodium, things like that. So even the blueprint for your very body, for your brain that is hearing and understanding this right now, this is the blueprint. It's made out of different combinations of these building blocks, of these types of atoms, of these elements. Now, how these can come together to create something like a human brain, science is still out on that one, but it always trips me up to think, all right, my brain is made of this stuff, and yet it is capable of understanding this stuff. I don't know, really crazy to think about. So this is a chart of all the known types of elements, the known types of atoms, and we can use it to determine lots of things about their properties. First thing I want you to notice about the periodic table is that it's organized into what we call periods and groups. So the periods are the rows. So I would call this period 1, hydrogen, helium. Period 2, lithium to neon. Period 3, sodium to argon, and so on and so forth. There are 7 periods. And then the columns going down are known as groups. Group 1, Group 2, Group 3, all the way over here to Group 18. What I would like for you to know is that elements in the same group tend to have similar chemical properties. Elements in the same group tend to have similar chemical properties. Now, the only exception to that really is hydrogen. Hydrogen does not belong with group 1. Hydrogen is kind of shoved over here. In reality, hydrogen kind of belongs, hydrogen's family, so to speak, on the right side of the table. But we start the table here in the upper left. Just like a book, by the way. You always read the periodic table like a book, going left to right, and then down, left to right, down, left to right, down. That's how it's organized. Notice that it's organized too by type of element. It's color-coded based on types. So this peach color over here, this orange color, those are the alkali metals. This light orange color, alkaline earth metals. This kind of yellow-orange color, these guys right here are other metals. This yellow-green color here, these are the transition metals. The lanthanides and actinides are down here. The metalloids, sometimes these are known as semi-metals. That starts with boron and it kind of stair steps down here to polonium. The non-metals are here. Halogens and noble gases. Halogens and noble gases are also types of non-metals, but they are a more specific type. So generally speaking, if you were paying attention to all of that, in the middle of the table and to the left, I have metals, what are classified as metals. Alkali metals, alkaline earth metals, transition metals, other metals. And then stair-stepping here in green, these are the metalloids or semi-metals, and then to the right of them are non-metals. So the simplest way of thinking about it is that on the right side of the table we have non-metals. In the middle and on the left we have metals. And then stair-stepping, separating those, are semi-metals. Semi-metals share properties of non-metals and metals. Metals in the middle and on the left side of the table are very, very good at conducting heat and electricity. Copper wire, that's why we use copper, sometimes aluminum, things like that, to transmit electricity. Non-metals are not good at that. Metals tend to form compounds that are solids at room temperature. Non-metals tend to form compounds that are liquids or gases at room temperature. Things like this.